Wait, who actually is here right now? If it's less than 5 people, I'm just gonna. I mean, it is less than 5 people. If it's less than 5 people, I'm just gonna get you guys to watch the recorded video. Cause I'm too lazy to just talk. Uh, and I'm making your test right now. Eventually, I mean, it's not gonna be a set day. It's gonna be. I'll let you fill it out. It's gonna be on Google Forms and you're gonna complete it. And that's gonna be like your test grade. So that's that. You didn't hear anything about it because I didn't even put an announcement yet. This is like the first time I'm talking about it. I just, Jesus. I'll wait 10 minutes, and if not enough people show up, I'm just gonna get you. You guys can just watch the recorded lesson. It's it's whatever. Easier for me, to be honest. I might just have. I mean, I'll post the test probably Friday, and I'll post a review stream on Thursday. And I'll probably won't do streams anymore unless it's like really important. Why? Because not enough people are showing up. I don't feel like because like everything I'm gonna say is pretty much in the recorded lesson anyway, right? And the students are coming, like you, Freya, and Rowita. You guys don't need much clarification, right? And if you do need clarification, you have the motivation to ask me questions. Like like this is mainly for students that don't really know what's going on and they don't and if they're not and they're not motivated to ask me questions, like they'll be motivated if they watch the stream, right? Because it's easy. They just type out in chat. But if they watch in a recorded video, and they don't understand something, they don't know that they don't understand something, and they're not gonna care much to ask me any questions. They're not motivated to ask me questions for like Google Classroom or something. So that's what this stream is mainly for, but they're not showing up anyway. I'll wait 10 more minutes, and if I don't see people, then you guys can watch the recorded video. Then I'll tell them to watch the video. Like if someone comes in 30 minutes, like at 1:30, like if someone could come at 1:30, I'll tell them to watch the lesson video, and if they have any questions, my stream will still be up. I mainly this stream is up mainly for you guys to ask me questions. The people who show up to the stream don't really ask me a whole lot. I mean, Tahira does. Tahira asks me a lot of questions. I'm glad she does. She has like that motivation to ask me questions. Whoa, Rissa, this is a surprise. I didn't think Irissa would show up. You ask questions? You talk. You definitely talk. I don't know about asking questions. Did you just tell your teacher shut up? You know, despite me being behind the screen, I am your teacher. I mean, I'll start at 110. Like I'll start. I'll do it. I'll do the lesson at 110. Yeah, I'll start at 110. No, I cannot help you with government. That's not my specialty. Supple, supple. Kind of. What's supple mean? Supple. I know a bit about how government works. Like, but not exactly. You know, I didn't go to college to learn about government. I took a. I mean, the closest thing to government I took was U.S. history, college level. That was the closest. Hello, bestie. My first time seeing you in this, actually being here, I guess? Is that the right way to say it? I disabled notific. I get more emails a day from Google Classrooms. I get mainly in the form of late submissions. Like for example, like some students are turning in, are marking the attendance assignments late. I don't understand. You're If you're not here for the attendance day, don't mark yourself here for that day. You, I don't understand. But those are most of my notifications. Most of my notifications are late submissions. Then it's annoying me. I've had to disable notifications from Google Classrooms because I get so much. I should pay attendance? What do you mean pay? No, no, no. So we have to take no, no. We have to take attendance every day, and we have to submit the attendance every day. What do you mean? What do you mean for how is it annoying for some subjects? Math? How so? What do you mean you don't know? It's like we tell you on Google Classrooms when we're streaming. Sometimes I even preface it. Like I let you know beforehand what time, and I start the stream really early too. You can take a picture of it and then upload it, submit it. You don't have to write it. Yeah, you don't do this much work in class because you guys have never done this much. You guys didn't do the work in the first place. Come on. Yeah, just take a picture of like a loose leaf or something, and you're good. What do you mean you can't? You can't take a picture? All right, let's get started. Oh, you gotta type it? That's weird. That's a weird restriction. All right, let's get started. All right, I'm assuming this operates under the assumption, right? Hold on. So, so let's go. This is under the assumption that you guys watched the lesson video on series circuits, but even if you didn't watch the video on series circuits, it should still be fine. It still shouldn't be difficult for you guys. So let's talk about parallel circuits. So Friday's lessons was on series circuits, but let's talk about parallel circuits now. All right, and so in this picture right here, in this diagram right here, this is how you're going to see things on the regions, or rather on regions questions. They represent the battery with these doubled lines here, and the negative side is the short line, and the positive side is the longer line. All right, so and the current goes from the positive. Well, it says the current goes from the positive side, but that's not really how it works. But let's humor ourselves just for now. So they'll go here for the resistor 1, resistor 2, resistor 3. And you'll see that all these resistors are connected in parallel. All right, all these resistors are connected in parallel right here. And so a real life version example of this would be this lamp right here. All right, this lamp right here. So these two light bulbs are connected in parallel. Again, resistors can be any electronic. Anything that requires electricity it can be considered a resistor, right? Because anything with electrons flowing through them, well, slows down the flow of electrons. Okay, so these are parallel circuits. Again, here now here here. So the difference between series and parallel circuits is like so. Again, we know that electrons go from the negative side to the positive side. Uh, so make sure you guys are paying attention. Please stop talking. I can't believe I'm saying this. I can't believe I'm saying stop talking in the stream. Like, what? Who am I fighting over? Well, okay. But again, these are parallel circuits, series circuits. And so if you take a look at this cord, I'm sure you've seen this cord somewhere, right? Maybe you've seen this cord somewhere. Maybe you have it at home, maybe at school. But when you connect electronics to this cord, you're connecting them in parallel. So each of these things are connected in parallel and not series. All right. So let's move on. Now, again, this is what it's going to look like on a Regents. Again, this image right here, this depicts the flow of electrons accurately. So it's going from the negative side to the positive side. So resistor 1, resistor 2, resistor 3. And there's current flowing through each of these resistors, okay? Current flowing through each of these resistors, and this is a series circuit. So yeah, you can think of these resistors as light bulbs. Any electronic is a resistor, any electronic. All right, any electronic that has electrons flowing through it, it can be considered a resistor. And then we discussed this on Friday's lesson. Well, if you watched Friday's lessons, if you watched the video. And so you have Christmas lights, right? If you have Christmas lights, if you have Christmas lights connected in series, what's going to happen is that if any one of these light bulbs break or you cut the wire, then everything else is going to stop working, right? If you just break one light bulb, electric current cannot flow through any of these anymore. But when you connect things in parallel, even if one light bulb burns out, even if one light bulb breaks, electric current can still flow through the other wire. So even if this wire is broken, if this wire does not allow electricity to flow through anymore, well, each of these other wires is going to allow electricity to flow through. So even if one is broken, the other ones still work. And so this is one of the benefits of circuits connected in parallel. This is how a lot of things are connected in real life. Well, most things in real life are connected in series and in parallel. It's a combination of the two. So it's not just either one or the other. It's it's a parallel series, and that's a bit more complicated, something you don't really need to know. Well, it's not too complicated. It's just it's connected in parallel. For example, yeah. So if you break one bulb, all of them won't work anymore. Because this is how, and I'll show you. So if you take a look at this light bulb, I just Googled it. Let's Google the diagram. Uh, so you have, if you have this right here, you have a circuit, electricity going through this. If this filament breaks, then the electric current doesn't move anymore. Because the wire goes up here, goes through this wire, goes to this filament, goes back down, and then continues to the other light bulb. So if you break this connection, if you break this filament over here, if the light bulb burns out, then no more electric current is going to flow through the wire anymore. Yeah, so the current stops. But a lot of modern light bulbs have a shunt. Hold on. Well, a lot of modern light bulbs have like a shunt, like another piece of metal wire at the bottom. So even if the filament breaks, even though the light bulb might not work anymore, it might not produce light anymore. There's like a shunt, there's like a wire at the bottom that still allows electricity to flow through. So even if one light bulb burns out, the other ones don't burn out. I mean, the other ones still work. So electricity can still pass through like a secondary wire here, but the filament is the one that produces the light. So the light bulb won't work anymore, but electricity will still pass through it if there is another piece of metal wire around this round at the bottom. So that's how some things work. And hold on. And these are Christmas lights connected in series parallel. So for example, you have there are four parallel lines right here, but then in each of these lines they're connected in series. So let's say if one of these light bulbs on the top breaks, then this whole line breaks as well. I mean, the whole line doesn't break. The whole line stops working if one light bulb breaks, but the other lines still work. The other Christmas lights still work. Yeah, pretty much. It's also if you ever in school classrooms, if you ever notice like a light dimming or a light one panel of lights doesn't work, that's because it's connected in parallel, right? If one panel doesn't work, it doesn't mean all the other panels stop working, uh, because it's connected in parallel. And in that panel, you see series. You see, I forgot exactly. I'm basing off memory, but it should be connected in some sort of like series parallel, type thing. I forgot to add this to the PowerPoint. I forgot to add this to the recorded lesson, but that's whatever. I'll add it later. All right, now let's get to a parallel circuit. All right, so you have, so this is on your reference table, on the fourth page of your reference table, this is what you're gonna see. Right here, fourth page of your reference table. And for parallel circuits, the parallel, current, voltage, and resistance are all defined like with these formulas in a parallel circuit. I'll talk to you guys more about what these formulas actually mean. All right, let's actually talk about what they mean. So let's talk about this. So in parallel circuits, this formula is saying that the total current is equal to the current running through resistor 1, which is I1, plus the current running through resistor 2, which is I2, and current 3, which is not in this GIF right here. So the total current running through each of these resistors, well, running through the entire circuit, is equal to the individual currents running through the resistors through these light bulbs, right? And so if you kind of take a look at this conceptually, well, you have a small amount. That's not how it works, Arissa. If one light stops working, the other gets brighter. That's not how it works. So yeah, the current splits equally. The current splits equally. I'm not sure if Irissa's on live or not. But you see a certain amount of electrons here. And then as it goes through each resistor, you see the amount of electrons splits up. So you can kind of conceptually see that, well, the total current running through the entire circuit is equal to the individual currents running through each resistor. So they split up and then they add back up. All right, so that's the total resistance. All right, I mean not total current. So the total current is equal to the individual currents running through each resistor. All right, let me know if that makes sense or not. Let me know before I move on. No, because you already broken the wire. Here, let's go back to, I'm sorry, I didn't stop here. Let's go back to this circuit right here, right? And the difference between series and parallel circuits. A light bulb breaking is pretty much the same thing as removing the wire, right? If you cut the wire, then no more electric current can go through anymore because you don't have a connection anymore. Hold on. So take a look at this, right? Yeah, if you cut the wire of an individual light bulb in a series circuit, then the whole thing stops working. No, it just won't go to that terminal. Hold on, I'll show you what I mean. Not terminal, that's a bad word for it. So let's take a look at this diagram right here, right? Actually, that's the diagram. That's fine. I can use this one. Um, so you have a light bulb here. You have a light bulb here, and you connect this switch. If you connect this switch and this wire connects to this part right here, you're gonna have a flow of electricity through this light bulb. But if you have another light bulb in parallel and this switch is not connected, no electricity is gonna flow through this. So no electricity can flow through this wire because nothing is being connected. And that's pretty much the same thing as a light bulb being broken. If this light bulb wire was broken, that's the same thing as this. No electricity can flow through this side. But if this wire was connected, if this switch was connected to this part right here, then yes, electricity can flow through. But if a wire is broken inside a light bulb and there is no shunt, there's no secondary wire, then no electricity can pass through that light bulb. So if one light bulb in a series is burnt, then that entire line of light bulbs will not work anymore, which is one of the cons of having things connected in series. And if you want to make sure everything works, even though one thing breaks, you want to connect them in parallel. Which is, so again, if you can think of it in this diagram as well, if one of these resistors stop working, then electricity cannot pass through the entire part of the circuit anymore. Yeah, in parallel it would work. Yeah, in parallel, the light bulb itself, the other light bulbs still work. It's just that there's no electrons passing through it if it's in this series. But in a parallel, it doesn't matter if one of these resistors stop working. Electricity, there are other pathways for that electricity to travel through the circuit. Yeah, yeah. So it won't get any more electricity because there's no connection. Yeah, pretty much. Yeah, Rorita, you're right. Yeah. All right. Any questions on current, the current total current thing? I think the GIF is self-explanatory. I think the GIF is pretty self-explanatory. All right, let's move on to voltage. Uh, I think this GIF is self-explanatory as well. You take the same concept as series circuits. And again, ignore the protons. Just ignore the protons. Yeah, let's just ignore the protons. And so these windmills right here are resistors, whatever these things are. I don't know what they are. But the voltage drop across every single resistor, the voltage drop across resistor 1 and the voltage drop across resistor 2, they're equal to each other. Okay? The voltage drop across both of these resistors are equal. It doesn't matter what the resistance is. Doesn't matter what the resistance is, the voltage drop is the same. Because if you take a look, the beginning of the circuit has a certain amount of electrons, right? A certain amount of electric current. And at the bottom, you have the same amount of electric current as well. So potential difference. Voltage is your potential difference. So the voltage drop, the potential difference, the difference in electric current is still the same. Voltage is the amount of uh, electrons, or rather, the amount of electrons there are. That isn't a good way to think about it. Voltage. Your voltage is just the difference in pressure. It's the difference in amount of electrons. Right? You have a high voltage, you have a high density of electrons. Yeah, yeah. It what is causing that? It's the amount of electrons you have. Yeah, it's going slower, but there's still a difference in voltage in potential. It's going slower, so you can kind of think of it like this. You have if you blow air, hmm, hmm, huh, uh, I'm trying to think of an analogy. I'm thinking of multiple analogies. I'm thinking of multiple analogies right now. Yeah, the 30 ohm resistor resists the current more. Well, yeah, it's just that it travels slower. Yeah. I mean, if you're fine with that, Furiha, I can move on. I think this next thing should explain it a bit better. But the idea is that the voltage drop is still the same, right? The voltage drop is still the same. You can think of it this way. If you have a wall, hmm, let's say your bathtub, for example. Let's say your bathtub, for example. Your bathtub is maybe it's small, maybe it's low height, but it doesn't overflow until a certain point, right? It doesn't overflow until a certain point. So you can say that the resistance of the bathtub is high because it's going to take a really long time for all the water to overflow. But let's say you have a lower height of a bathtub. Let's say your bathtub is lower height. It's going to take less water to overflow, right? And so that's a lower resistance. And so while the overflow rate, once it overflows, is still the same, it's just that the resistance is higher. The bathtub has a higher height, and so it's going to take longer. It's going to take more water to overflow. I'm not sure if that's a good analogy. I'm trying to think of an analogy, but it's not. That doesn't explain it that well. Hey, maybe this next analogy will be better. So again, in a circuit connected in parallel, let me give you an actual image. So series connected in parallel. All right, series is connected in parallel. Now, if you take a look at this formula right here for resistance, take a look at this formula right here for, and again, before I preface this, a lot of these things are very hard to understand. Like I'm trying to think of an analogy to help you guys, but let's look at this resistance formula, right? So this is what it says on your reference table. So why does it say it like this, right? Why is it inverted, right? Why are all these resistances on the bottom? Well, let's think about this conceptually, right? Let's think about let's look at this picture right here, right? Let's take a look at this picture right here. And so there are this is an escalator, and there are stairs. I think these are stairs. I'm pretty sure these are stairs on the right-hand side. And let's take a look at all these humans, and let's say these humans are all electrons, right? Let's say these humans are all electrons. And these escalators, these stairs are resistors. Whatever resistors they are resistors. All right. And there is a certain amount of electrons on this side, and all these electrons on this side want to get all the way up here, right? They want to get all the way to the other side. But there's a bottleneck. Even though there's a mass of electrons over here, this resistors, there can only be a certain amount of electrons that flow through each of resistors at a certain amount of time. You see that this escalator is doing there's a double file of people, like there are two lines of people going up this escalator. So we can say that the resistance, let's say the resistance of this escalator is small because there's more electrons flowing through it. And these stairs has a higher resistance because there's less people walking on these stairs, right? So there's less electrons. So there's a higher resistance here and lower electron current. Low resistance here, more electrons are going through. But this is being bottlenecked here. If you ever been in Penn Station, if you ever been in maybe taking the 7 train to like 42nd Street, Grand Central, or any subway station, you see that the stairs are like packed, right? There's the stairs are packed, right? Escalators are packed. You're stuck waiting there to get onto an escalator, and that's a bottleneck, right? That's a bottleneck. But what happens if you add a third resistor, right? What happens if you open this escalator? What happens when you add a third resistor? Well, when you add a third resistor now, these electrons have another pathway to go up here, right? There's another pathway. There's another pathway now. So the fact that you just added a third resistor, a third pathway, you are allowing more electrons to flow through the circuit now. More electrons are now flowing through the circuit because you added a third resistor. You added a third resistor, and so now more electrons are flowing through. So the more resistors you add, the more electrons can flow through, which reduces the overall resistance of the circuit, because the more electrons you have flowing through something, the lower resistance you have. No, that wouldn't burn it. The only way things are gonna burn, no, because there's only a certain amount of space for because there's only a certain amount of space for electrons to be, and the electrons are repelling each other in the first place, right? They're repelling each other in the first place, so there's only a certain amount of space they can be in. The only way you're gonna burn something is if there's really low resistance and your electrons are traveling too fast, right? That causes things to burn. That causes a lot of heat to be generated due to friction. And that's why a lot of things you want resistance. You want some resistance so that your things don't start burning up. And so these are in parallel. Not work anymore. No voltage, broken wires, broken circuits. That's the fastest thing I can think of. It's gonna work if there's a metal connection, right? If it's connected, it's gonna work. The only way something won't work is if there's no voltage or one of the resistors is broken, which is not allowing electricity to pass through it. And so that's why this formula is like this, right? That's why this formula like this. And the math proof is over here. Yeah, electrons cause damage. They cause damage. Because electrons is electricity. The flow of electrons is electricity. And this is the same thing as and if I were to and this is why your voltage difference, there's the same voltage drop. You'll figure it out, Rowita. It's just using math. You'll figure it out. Uh, but this is also why your voltage drop is the same, right? Because you're just getting bottlenecked here. The voltage difference is the same. It's just that through these resistors, there's just a lot more bottleneck, right? It's still going at the same. Rather, there's more electrons flowing through here than here, but the difference in voltage is still the same because you're getting bottlenecked. It's it, and if that doesn't make sense, it's just gonna take some time for you to think about it, right? It's gonna take time for you to understand. You can't just expect to get it instantly, and then especially since electricity is something you can't see. It's a lot of conceptualization and thinking. There's only so much I can do with analogies to help you guys. There's only so much. The electrons, well, there's only a certain amount of current that you're having. You slow down to the rate at which, well, the entire current, which is electrons are slowing down. It's the entire current of the circuit. The entire current of the circuit is the same. It's not about slowing down or not. It's that the speed throughout the circuit is the same. It's just that when you add these resistors, the circuit adjusts. There's a sort of equilibrium, right? When you add resistors, it'll come to an equilibrium of some sort. Now, if you were to, if I were to say, if you were to say, if you removed one of these resistors, yeah, then your electrons would slow down, right? Oh, rather, hold on. Your electrons would slow down. I don't think that's right. I'd have to do some math. It's PowerPoint's online. I mean, the PowerPoint's on Google Classrooms under a different topic, under circuits of magnetism. I'm not sure. I'd have to answer your question, Arissa, I'd have to do some math. But your current would only change when you add another resistor or or remove a resistor. Because the current is already in equilibrium. If you've left the circuit there for a long time, it's already in equilibrium, right? The current is already adjusted to some level. The only time your electric current changes is if you remove a resistor or add a resistor and measure the change in current. And again, resistors are light bulbs, anything that are electronics. That's unfortunate, Josh. You came in the middle of everything, I think. You came in the middle of it all. I'll explain it to you after this, but yeah. Let's do some practice questions. Also, the proof, Rita, it's not complicated. I'm it's not even a proof because it's not using calculus. I'm I'm just using algebra in that proof. So number one, a combination of two identical resistors connected in series has an equivalent resistance of 10 ohms. So this series is the circuit is in a series, right? And it's saying that when two resistors are connected in series, their equivalent resistance is 10 ohms. And so we know that in the formula on your reference table for series circuits, it says in series circuits, your equivalent resistance is R1 plus R2 plus etc. Alright, so it's in series circuit Req is R1 plus R2. And it's saying that these resistors are identical. Right? These resistors are identical. So that means that if my resistance or my equivalent resistance is 10, then R1 is 5 and R2 is 5 because they're the same. Alright, so R1 is 5 ohms, and R2 is 5 ohms as well. Now the second part of the question says, what is the equivalent resistance of the combination of these two same resistors when connected in parallel? So the formula for equivalent resistance in parallel, when you connect them in parallel now, honestly, you guys would understand this if you play with circuit boards in lab. Like playing with circuit boards in lab helps you understand this very well, because then you can actually see the actual like voltage and current change. But you guys can't see it, which is unfortunate. So the equivalent resistance on the parallel circuit is written like this. All right, so 1 over Req is equal to 1 over R1 plus 1 over R2. All right, so we know R1 is 5. One over 5 plus 1 over 5. Okay, so 1 over 5 plus 1 over 5 is 2 over 5. You can make a ratio here, because if you divide 2 by 2, you get 1. So 5 divided by 2 is 2.5. Or you can cross multiply. All right, you can cross multiply. So 5 times 1 is 5. 2 times Req is 2 times Req divided by 2. And you get 2.5 ohms is equal to Req. So you can see a concept here. When you connect two resistors in series, the equivalent resistance is 10 ohms. But then when you connect them in parallel, your equivalent resistance decreases. Right? So it's 2.5 now. Any questions? Hello? Hello? Can I move on to number 2? Number 2 is a conceptual question. And so it's saying a 3 ohm resistor and a 6 ohm resistor are connected in parallel across a 9-volt battery. Which statement best compares the potential difference across each resistor? Okay, so they're asking you what is the potential difference? Potential difference is your voltage, right? So they want to know voltage 1. How does voltage 1 across a 3 ohm resistor compare to the voltage across a 6 ohm resistor? All right, well, there's an easy way to think about it because it's in your reference table. Says in your reference table for parallel circuits, because it says it's connected in parallel, your voltage is the same throughout. So your total voltage is just the voltage running through 1 is the voltage running for 2. So it's all the same. All right. So it's one of these choices. Which choice is going to be? So it says in your parallel circuits, right, your V is equal to V1 plus V2. Oh, no, not plus. Oh, that's a huge mistake. Is equal to V2 is equal to V3, etc., etc. So your voltage is the same throughout. Nothing's different. Where did Bestie go? That's what I'm confused about. Where did Bestie go? All right. Number 3. Number 3. What is the total current in a circuit consisting of 6 operating 100-watt lamps connected in parallel to a 120-volt source? So the power of each lamp, we're gonna call it power 1, is 100 watts, and you have 6 of them. So there's 6 lamps, and your voltage is 120 volts. This is actually not a huh. This is actually not a circuit, a parallel circuit question. This is actually electric power question, but whatever. And so they want you to find out what is your total circuit, total current. All right, so you know that on your reference table, the formula has power, voltage, and current. Is this right here? So that's the only formula that has power, voltage, and current in it. All right, power, voltage, current. And so they want the total current. So you know the. Oh, I guess there is a reason why it's a parallel circuit question. And a parallel circuit question, your total current is equal to I2, I1 plus I2 plus etc. So you're gonna add all your power together. So since you have 6 lamps, you're gonna do 6 times 100, 600. V is 120, and I is I, divided by 120, divided by 120, and you get 5 amps. That's your current. Perfect. Four. 3 identical lamps are connected in parallel. If the resistance of each lamp is X ohms, so R1, R2, R3 is X ohms, what is the equivalent resistance of this parallel combination? And so again, on your reference table, you'll see this formula, right? Now, so R1 over REQ is equal to 1 R1 plus 1 over R2 plus 1 over R3. So 1 over REQ. And we know that resistance 1 is X ohms. X plus 1X plus 1X. Because again, they're all X ohms. Add all these together. Probably going to run out of space. You get 3 over X. Alright, you get 3 over X. If you want to cross multiply 1 times X, you get X. X 3 times REQ, you get 3 REQ divided by 3. So REQ is equal to X over 3 ohms. Alright, that's fine. That's 4. That's number 4. Any questions? Alright, let me know if you're ready to move on. I flipped it because 1 over R. Wait, why did I flip it? I mean, okay. I flipped it because you get. Hold on. Let me make this more clear. So when we saw that we got 1 over REQ, right, is equal to. What did we get? I'm pretty sure it was like this. No, it wasn't. It was 3 over X. I flipped it because we want REQ by itself, so we have to cross multiply here. We have to cross multiply. So 1 times X, you get X. 3 times REQ, you get 3 REQ. And then we want REQ by itself, so you have to divide by 3. So you get X is equal over 3 is equal to REQ. And that's your answer. Alright. We ready to move on? Sure. 5. Electric circuit contains a battery, 3 lamps, an open switch, as represented in the diagram below. So when the switch is open, there's an electric current in what? So again, you have, it's kind of the same thing as a lamp. So you have a lamp here, and you have, and this is over here. That. So lamp 1, lamp 2. I'm gonna just lamp 3. Just pretend that's 3. Actually, I'm just put number 3. So if this circuit is open, if this line is not connected, if the circuit is not connected to this part, then no electrons can go through, right? There's no connection here, so no electrons can go through. So the only electric current, the only lamp that will have electric current going through it is going to be lamp number 1. So there's only going to be electric current going through lamp number 1, right? Because that's the only pathway. There's no connection here, so there's no electrons can go through this side all the way to this side. So no, there's only electric current going through there. There are no electric currents going through these other two lamps. So it's only lamp 1. Only lamp 1. Now if this circuit was closed, if this circuit was now connected, right? If this circuit was now connected now, then yeah, electric current would flow through now. Electric current would flow through because it's now connected. But because the circuit is open, there is no electric current. Let me know when you want me to go through. 6 is the same thing. I would do 6. 6 is a kind of using the same logic. 7. Let me know if you have problems doing 7 and 8, and I'll help you guys. But you guys can do 7 and 8 yourselves. 6, 7, 8, it should be something you guys can do yourself. And I'll be here. I believe in you guys. That is not sarcastic in the least. Uh, 5? Yeah, 5. Here. Here. If you look at the top, you see a switch. That's kind of like an off and on button, right? This is the on and off button, basically, essentially. If you open this switch, which is like that, that's open. This is closed. Open, closed. So when you open the switch, you don't allow electrons to flow through. Okay? If you don't open the switch, you don't allow electrons to flow through. If you connect the switch, then electrons start flowing through. So if you take a look at this diagram right here, well, if this switch is open, then no electrons can go through lamp 2. No electrons can go through lamp 3. Because the electrons have to go here, here, and then over here, and then there's no connection here. There's no connection here at all. So the only place the electrons can flow through is through lamp 1, because there is a connection from lamp 1 to the end here. There has to be a connection from the negative side to the positive side for there to be an electric current. If you do not connect the switch, electrons do not flow through this wire, through this circuit. Let me find another GIF. I'm sure I can find another GIF. I mean, I can make this. I can show this using FET. I just don't want to make a FET diagram right now. Current moves from negative to positive. It doesn't matter either way, but current moves from a negative to positive. The shorthand side is negative. I think it's on your reference table. Yeah. So the short side right here for a cell in the battery. The short side is negative, and the long side is positive. So if you see a positive end, that's positive. If you see a long end, that's positive. Short end, that's negative. Make that. I'm too lazy to make the FET, to be honest. How long will that take me? Take me a long time. No, not a long time. I'm just too lazy. Did you just call me Rachel? You just called me Rachel. All right. Guess I'm not helping Arissa anymore. I didn't know your last name was Mulani. Isn't it Walcott? Iris. Iris Mulani. Oh yeah, Joshua, are you still here? Cause I'll help you if you need help now. Like I'll go for the entire lesson again, or if you're watching the video, I can just go for the entire lesson again. Let's talk about my name. It's from my Chinese name. Well, the first part of my Chinese name means rich, so. Iris, are you done with the questions? So I can stop paying attention to the stream now? Alright, make sure come on, let's get through this. What's two? You don't understand seven. Well, let's take a look at the formula. It's actually conceptual because I explained the thing with the elevators, right? If you're connecting them in parallel, no, you don't both increase. Think about connecting something in parallel, right? Pretend pretend the, let's look at this picture, right? You're pretending the elevators are resistors, right? And you're pretending the humans are electrons. Well, if you add another elevator, what happens to the flow of electrons? Well, first off, if resistance and current is inversely proportional, that's the first thing you need to understand. So they both can't increase, right? That's the first thing you need to understand. They're inversely proportional. So if one thing goes up or down, the other thing does the opposite. So, but let's say what happens if you increase the amount of resistors, if you increase the amount of elevators? Is it easier for humans or electrons to flow through now, to pass through, or is it harder? Total. I guess in this situation it can mean total. Yeah, sure. I think it's easiest for you to think about equivalent as total resistance across the circuit. Yeah, because if you add more elevators, it's easier for there's more paths for electrons to move. So if you add more resistors in parallel, this is also only for parallel, by the way. This is only for parallel situations. So if you add, and what does the question say? As the number of resistors in a parallel circuit is increased, what happens to the total resistance of the circuit now? Because, right? So when you add more resistors, when you add more escalators, it's easier for things to travel through, right? Well, there are more things can travel through now. So your total current increases, right? So your total current increases. And because your total current increases, well, that means the total resistance, the equivalent resistance of the entire circuit decreases. Because the less resistance you have, the more current will flow through, right? The less resistance you have, the more current will flow through. I think that I'm not just gonna tell you what 8 is. Like, tell me what you think 8 is. What do you want to find out? What do you want to find out number 8? You want to know the formula? I'm gonna give you a reference here right now. You wait, what do you want to know a formula for? Well, tell me what you think it is. Tell me what you want to know. Yeah, right. What do you want to know? What is the problem asking you to solve for? Right? One? Solve for one? What? What do you mean? You think it's one? I cannot tell me how you. Okay. What does the problem want you to solve for, Irissa? Tell me that first. That's what is it though? It's actually in the problem. This shouldn't be difficult, Irissa. It says in the problem what you want to solve for. Ampere is a unit. Current, right? And so we measure current in amperes, so we want current. What do you know? What else do you know? What do you know in this problem? What are you solving current through? For what? Bestie, I think if you return like an hour later, I don't think that helps. It's a 4 it's 4 ohms. So what is that? What is that exactly? Is it IVR? What is it? Oh, that's good. I'm glad you're watching it, Bestie. So what is 4? What is 4, Arissa? No, it's just R. It's because there's one resistor here, right? Because it says 4 ohms. So through the 4 ohm resistor, so they want the electric current running through the first resistor only. That's the only thing they care about, right? Running through the first resistor, not anything else, just the first. What else do you know? What's V? What's your voltage, right? Because there must be a battery here. Otherwise, if there wasn't a battery, no electrons would be pushed through. It says in the diagram what your voltage is. What is your voltage? Voltage, volts. Your battery has a voltage. 12, yeah. So your voltage is 12 volts. And since we know that in a parallel circuit, in a parallel circuit, you know that current voltage is the same through every resistor, okay? Voltage is the same for every resistor in a parallel circuit. So you're going to set up your equation right here, right? So R is equal to V over I. And that's your answer. And you should be able to solve it. All right. Bestie, do you have any questions for me? I mean, I'll still keep this stream up until 3. I won't talk until someone asks me any questions. I want to do something in the meantime. It's negative positive always. Reasons is always negative positive.